like about the video that I'm showing, it's showing you some three-dimensional visual of cylindrical method before we build our own cylinder for cylindrical method. So I'm going to play this video. Just pay attention to how they are shaping it. You may take notes, but you may not. I just want you to get some visual idea of what cylindrical shells method is. So I got a chat. So I said you may or may not take the video of take the notes of the video. It's more for seeing how that works.
Professor Dave again. Let's talk about cylindrical shells.
So do you hear that? Do you hear when I was playing it? Yes? Cool. Okay. So let's do that.
Professor Dave again. Let's talk about cylindrical shells. We just learned how to find the volume of a solid of revolution by integration, just the way that we calculated the area under a curve by running a line segment of varying length across the region and adding them all up. To get volume, we just ran some area across a shape and added all of those up. Sometimes this was the area of a disk, sometimes the area of a washer. But whatever the situation, we were able to calculate the area of a cross-section rather easily given the functions involved. Sometimes it won't be so easy to use this method, so let's look at an example where another method will be a better approach. Take, for example, y equals 2x squared minus x cubed. The region between this function and the x-axis looks like this. Let's say we rotate this area around the y-axis to get this bundt cake looking thing, a solid of revolution. A cross-section of this solid would be a washer, given the empty middle region, which we can then push upwards from the base to the top of the solid. But the problem is this. When we did this before, the functions were simple, like y equals x or y equals x squared. And given that we are doing things in terms of y, with the previous method, we would have to rewrite functions in terms of y so that we can integrate. With the other examples, that ended up being no problem, and we were able to get expressions for the inner and outer radii of the washer that we could integrate. Here, it's not so easy. Rather than one function per radius, here, both the radii depend on this same function. And furthermore, solving this function.
So I want you to pay attention that the left and right, or right and left of, if I was saying right minus left, do you remember when I was rotating, or when we were rotating the washer, we said left function minus right function minus the left function, and then you would rotate that, or you would find the length. They are both coming from the same function. So if you look at here, right and left of the function are coming from the same function. So that's going to be an issue. So you may not use the method you learned in 6.2, which was disk or washer. So that's why this method would apply here.
For x in terms of y is not a very appealing task. But there is another technique we can try, and it is called the method of cylindrical shells. Before we apply this to the problem at hand, let's just look at this hollow cylinder. This has an inner radius, R1, which ends at the inner face of the solid, and an outer radius, R2, which ends at the outer face. This cylinder also has a height, h. To get the volume of this figure, we can calculate the volume of the cylinder using R2, pretending that it is solid all the way through, and then subtract from that the volume of the inner cylinder using R1, since that's all empty space. The formula for the volume of a cylinder is pi r squared h. So let's do pi r2 squared h minus pi r1 squared h. Factoring out pi and h, we can turn this into pi times the quantity r2 squared minus r1 squared times h. If we remember how to expand a difference of squared terms from algebra, this term is equal to the quantity r2 plus r1 times the quantity of r2 minus r1.
So what you see here, it's the proof of the cylindrical shells method. So you're gonna see that we're gonna use the result of this one in order to use cylindrical shells method. So basically what we are doing here, we started with volume of the outer minus the volume of the inner to find the volume of the shell in between them. So for now. So whatever you see as a result of this proof is what we're going to use for our examples in 6.3.
Here's the clever bit. Let's take this sum and turn it into an expression for the average value for the radius. To do that, we just divide by 2, but in order to keep the same value for the equation, let's put a 2 at the front. Since this is now the average radius, let's just call it r. Then over here, the difference between the radii gives us the thickness of the cylinder. So we can call that delta r if we like. And like that, the volume of this cylindrical shell will be equal to 2 pi r h delta r. One easy way to remember this is to see that 2 pi r is the same as the circumference of the cylinder. So this is really just circumference times height times thickness. The reason this is useful is that we no longer have to solve for x in terms of y.
So I want you to look at the visual of how cylindrical adding all these thickness of the cylinders together would add us to or would give us the volume of the solid. So just look at here.
If we picture one possible cylindrical shell, it will have a height that is equal to the function f of x and a circumference 2 pi x. As this shell spans the volume, we then simply have to integrate 2 pi x times f of x dx. In this case, f of x is 2x squared minus x cubed, as we said. So let's plug that in for f of x. And then to simplify, we can take 2 pi out of the integral, but the x must stay, and it can be distributed across the other term. That leaves us with 2 pi times the integral of 2x cubed minus x to the fourth dx, evaluated from 0 to 2.
So I'm going to replay this part. I want you to write down this formula. I'm going to write down this formula as well for you on my notability. But then this was a proof of why we are using this formula. And every time we need to replace r and h and dr by being y or x or its equivalent, we're going to talk about that. But there was an outer radius, inner radius. So you found and the height is h. So total volume is the volume of the outer minus inner. And then they factored r square, r1 square, and r2 square subtraction into r2 plus r1 and then r2 minus r1 right there. Right here, and then multiplied outside and inside, divide inside by 2 to undo. So this is r2 plus r1 over 2. So it's average of these two r's, which we're going to name it r. And then for the difference of r2 and r1, that would be this little thickness here. So it would be a thickness here that it's going to be either dx or dy from now on. So I'm going to name it dr for now. And that's why we came up with this formula. This formula is something you need to have on your paper and then have this shape in front of you as well. So I want you to have this shape and this formula written down. So I'm going to give you a minute. I don't know if you have a question or someone's audio is on mute. So if you have a question, feel free to ask me. Otherwise, please mute yourself. So, so what I want you to do, I want you to write down this formula and I want you to graph this cylinder. Okay. So let's keep going. So now on this shape, do you see that you have a cylinder? So this time, instead of having the cylinder to be on the other side where was a washer method, so you have the thickness of all these cylinders being added together, and that would give you the area or the volume of the revolution. So because again, the two ends of the graph is coming from the same function, you will add up the thickness of all these cylinders together to get the volume of the revolution.
No longer have to solve for x in terms of y. If we picture one possible cylindrical shell, it will have a height that is equal to the function f of x and a circumference equal to 2 pi x. As this shell spans the volume, we then simply have to integrate 2 pi x times f of x dx. In this case, f of x is 2x squared minus x cubed, as we said. So let's plug that in for f of x. And then to simplify, we can take 2 pi out of the integral, but the x must stay, and it can be distributed across the other term. That leaves us with 2 pi times the integral of 2x cubed minus x to the fourth dx, evaluated from 0 to 2. We integrate to get 2x to the fourth over 4, or 1/2 x to the fourth minus 1/5 x to the fifth. We evaluate at 2, and we get 8 minus 32 fifths, or 40 minus 32 over 5. So we subtract and multiply by 2 pi to get 16/5 pi. So while this may have seemed complex, part of that is because we derived the formula for the volume of the cylinder. We won't have to do that every time. We just need to know that the volume of the solid with a cylindrical shell oriented vertically will be equal to the integral of 2 pi x times f of x dx over the interval that spans the solid. So we can see that for this particular example, this method ended up being easier than the washer method we used in the previous tutorial, as our formula for the volume of the cylindrical shell was ready to go, which meant we didn't have to do much to set things up. For any solid of revolution you are looking at, whether the cross-section is a disk or washer, you will just have to think critically to figure out which approach is best, depending on whether it is easy to find the radius or radii of the cross-section with the function or functions as given, or whether it is easier to express things another way. For a little practice with this new method, let's check comprehension.
So I want you to copy down this question. Y equal to x cubed minus 7x squared plus 15x minus 9. And then from 1 to 3, you want to find the volume of revolution about x-axis. Above the x-axis to find it around y-axis. So write down the question, and then we'll do that together as an example. I'm going to write it down on my notability. So write down y equal to, for this one, not every time you need to have the graph. Is not as critical to have the graph when you're using cylindrical shells method. Minus 7x to power 2 plus 15x minus 9. So you have 2 pi. So just think about it. 2 pi and then x, f of x dx. 2 pi x, f of x dx from 1 to 3. Just look at the
Thanks for
setup.
watching, guys. Subscribe.
So write down the setup. You don't need to do the calculation. Just for the cylindrical, the formula we had 2 pi r, which in this case is x, and then f of x dx. From 1 to 3. Okay. Are you all ready that we move on to some of our own examples? Okay. So let me share my iPad now. So that's a good question. Let's just look at here. Someone asked how being above x-axis would influence the answer here. So let me just show you on Desmos. So here you go. On Desmos, anytime you are dealing with, so this is the graph that you had there. Do you see from 1 to 3 would be from here to here? If they don't say above x-axis, so anything below this would also be considered, right? So you need to have a bounded shape in order to rotate it. So it is bounded from, and then, so when you say 1 to 3, it automatically takes it from being bounded by where it's intersecting 0 and 0, sort of x-axis. So it's more of reconfirming that you are not considering any area or anything below that. So yeah, so just sort of reconfirmation. And if I was regraphing this one, let me just graph that in Notability. So here was the graph. So from 1 to 3, it looked like something like this, right? This was 1, this was 3. I don't care about the rest of the graph. And they said bounded by x-axis as well. So this is the area you have, and you are rotating that. This is how I envision this one. So you're rotating this along y-axis, right? So you are taking basically what you are doing with cylindrical shells method, as it says from the name, you are adding the shells of all these cylinders. So infinitely many shells. You are adding the thickness of all these shells. And then same thing with the back here. So you are adding the thickness or the shells in between all of these to get the volume of the solid. Sometimes it's, I mean, many questions are doable with both washer and with this method, but then if both sides are coming from the same function, then cylindrical method is the only one. No, you could rotate along x-axis. I'm going to do an example that it's rotating along x-axis. It could be rotating about any other axes. So that's why it was important that I said, write down this formula, 2 pi RH dr. So just look at here how I would set it up rather just memorizing. Let's say let's say this is the shape you have, right? And then I'm going to take one cylinder here and I'm rotating that cylinder. Again, remember that you are rotating a cylinder considering the shell of that cylinder. So the thickness in this case is coming from dx. Do you all agree? The thickness of this cylindrical shells method. So on the exam that is coming up, for final, we may put it as a mix, but for the exam, for the first exam, I'm gonna say use cylindrical shells method, use washer method. So then at least give you some idea that you're using cylindrical shell. But so the thickness is dx. So what else you need to put in? So you have 2, so integral of 2 pi, that's always. R was what? R was the radius, the average radius of these two. R was, we said in average, let's say that is R, the radius of the whole thing. Since this time R1 and R2 are very, very close to each other. So that means, although you see it as two things, but we assume that all these shells are very, very tiny, that when we add these shells together, it's going to give us the volume. So that's why this is equivalent of R, which in this case, R is the same thing as X, because R is corresponding to the X value. If X value here was 2, then the R was 2. If I was picking another cylinder, whatever was corresponding X to that would have been my R. So 2 so far, 2 pi R, my R is X, times H. This is probably similar to what we had in washer too, but the H here, the height here is corresponding to the Y value in this case. Do you see that? Do you see the height is corresponding to whatever is the Y value? So the Y value is, in terms of X, was equal to what? Can someone tell me, or let me go to Desmos. X cubed, 7x squared. So the height here is x cubed. Was it minus 7x squared? Tell me the rest.
Minus 7x squared plus 15x minus 9.
Thank you. Minus 9. Yeah. Okay, did I copy it right?
Yeah.
Thank you. So plus 15x minus 9. So that's my H. You are not squaring. You're not manipulating that function at all. So it's just the height. You write it down. And then dr is this thickness that in this case is dx. Dr sometimes is dy if it's rotating along x-axis, and it's dx if you're rotating along any axis that is vertically like y-axis. And then you would say this dx will give me a clue that I'm going along x-axis. So if it's from 1 to 3, then it goes from 1 to 3. I would say cylindrical shells method is fairly easy if you set up correctly, or if you visualize it correctly from the beginning. I think it's a little bit easier than the other method, the washer method. Okay, let's do another example. And again, I'm going to do some rotation along other axes, so you would see how it works. Here we go. Find the volume. Find the volume of y equal to x, y equal to x squared, rotating about y-axis. Let's just graph it quickly. I'm sure you all know how to graph y equal to x. And y equal to x squared. And here is the intersection. It goes from 0, where are they intersecting? 1. Yeah, when you put x squared equal to x, you bring everything to one side, put it equal to 0, factor x, then x is 0 or x is 1. So those are the intersections. And the corresponding y to that would be 0 and 1, respectively. Okay, any questions? So now you want to use cylindrical shells method to find the volume. And you may compare if you were using washer method, but then cylindrical shells, just randomly take one cylinder and you are rotating it. It says rotate along y-axis. So you're rotating this cylinder along y-axis. This is dx because you are cutting the shell along x-axis. So I'm gonna write integral. The formula was saying what? 2 pi r h d r. So dr is clear. That's dx in this case. 2 pi is clear because that's a constant. So far I have these two things. Okay. Then what else? So let me just make my picture a little bit nicer with the pink one. So this cylinder has to be exactly on my curve because I'm adding all these things. In this case, it's 2 graphs, so make sure. Okay. So that's the corresponding cylinder. Okay. So far, you know these two things. The R, so in the formula, there is a R. That corresponds in this case directly to whatever is the X value there. So it's going to be X times, now you're talking about the height here. So this height, what is this height? Look at this one and tell me what is this height? Exactly. Exactly. So it's going to be the top function, which is x, minus the bottom function, which is x squared. So this height is x minus x squared. So x minus x squared. And it goes from 0 to 1 because that's along x-axis. Along x-axis, it goes from 0 to 1. You can copy that cylinder out and mark it, or you can mark it on the graph. I need to see some marking when it comes to the testing. Okay. I don't have the calculation. We can calculate. No, actually, I do have it. So your final answer probably should be pi over 6. As a final answer. So do the calculation. So you distribute x, you take the integral from 0 to 1, multiply by 2 pi, and that's it. Any questions? So do you see that you are adding the surface of, or the shells of the cylinder, and that is equivalent of 2 pi r h dr. 2 pi is easy to name. dr, depending if you are cutting horizontally or vertically, would be dx dy. And then for r and h, you need to decide. let's do another example. Any question here? Can I move on? Let's do one more. The next example says, find the volume rotating about x-axis, this time about x-axis. So rotating, so you want to find the volume is rotating about x-axis under the curve y equal to square root of x and above x-axis. Again, we are confirming that it's a bounded area that I'm rotating. Otherwise, the volume would be infinite. So it's not, you're not able to calculate it. So basically, and that would be from 0 to 1, from 0 to 1. So here is the graph. I want you to be well familiar with radical from 0 to 1, and then the output to be 1 as well. So it says the graph that is bounded here, you want to rotate that along x-axis using the cylindrical shells method. So using the cylindrical shells method, so you need to build cylinders this time that is rotating this way. So you have the thickness of the graph this way, rotating along x-axis. So now let's set up the integral. Again, by practicing, you would know what you're doing here, I guess. Okay, so 2 pi. This time the thickness of the cylinder that I'm adding them together, is it dx or dy? Excellent. It's dy because it's the thickness is from here, so it's dy. So the formula was saying 2 pi RH and dr. So now I need to think of R and H. R is the radius of any arbitrary cylinder that you take. So R would be this length. Do you agree that this length corresponds to whatever is the y value of, so y value of my function? Because that's the same thing as this. So this radius is the same thing as this radius and corresponds to whatever is the y value of my function, right? Do you agree? So this is R. So whatever is my y value of my function, that corresponds to that. So because this is in terms of y already, so I'm going to write y for that. So for the radius is just y. Instead of, do you remember for the previous one, the radius was x? So now the radius is y because that's corresponding to here. So far on the formula, you have 2, you have pi, you dealt with r, dr. Now we need to think of height. Height is this distance here. So what is this distance? Now you tell me, what is this distance? And remember that height that I'm writing here has to be in terms of y. So what is that measure? This is the line of 1. Tell me, what is this height? What is this measure? It comes from the difference of right minus left, 1 minus x, but I need to replace x in terms of y because I don't have x in parentheses. If I have x, then how do I get the derivative with respect to y? So, and then x, if I isolate x from here, x is equal to y squared. So in reality, that's 1 minus y squared. And it goes from along y-axis, so 0 to 1. So look at the setup here. And let me know if you have questions. So you would say right minus left. Of course, this is x, so it's 1 minus x, but the x that is corresponding to the graph, I need to replace x because I'm taking derivative with respect to y. Any questions? Okay, wouldn't 1 minus y to be a distance between the y-axis and the function? So look at here. So I have a question. So what is this total length to here? Let's just look at with, let me change it to green. What is this measure from here to here? One. Okay. What is this measure from here to here? Just the green piece. X, because it corresponds to the X value, whatever is along X-axis. But since it's on the graph with the X of the graph, so it's then, so then if this is 1, this is X, which is the same thing as y squared, then what is the remaining length? 1 minus y squared. Okay, great. Another question, when do we know when 1 is right or left? So you always say right minus left, top minus bottom. So what is on the right of your graph right now? So if I want to find this measure, what is the right and what is the left? So this is the right, this is the left. So, and then the right is corresponding to 1. Make sense? Yes. Any other questions? Jersey, do you have a question?
No, sorry.
No, you're fine. Any other questions here? So I want you to keep in mind the class, as I said, the pace of the class is pretty quick. That means your turnaround time to practice is pretty short compared to a regular semester. So that means you need to daily go over these notes. You have homework due tonight for up to, I think, 6-2. And this is 6-3. I would say if you finished it, get us started on 6-3 because it's important that you practice it. Okay, any question? So let's just talk about what your work would be for the take-home piece for that 1 hour and 15 minutes of independent work. before our time is over. Sure. So let me just go to, oops. Share my screen with you. Here it is. So 6-4 are work problems. So what I was doing here, so if you have time, we're going to do one more example of cylindrical shells today. But before that, let me tell you what is your take home. So go to modules. Under modules, click on 6-4 work. I will put one question on the test from the work, pretty much one question or more per section, but at least one from work, or maybe just one from work. There is a video here if you want to watch, but the ones that I created was number 2. It says video of lecture notes, about 15 minutes. So I went step by step through work, explaining the basics. And then in physics, how it works. So writing out the formulas and so forth. So for the first 14 minutes or 15 minutes is the concept of work. Then I was putting YouTube videos of myself going over multiple examples. Some of these examples are coming from the worksheet you see under the note, but the examples have been written. So as you see, I went through step by step explaining of how that works, how to set it up, how to write it out. So there are 2 videos. So a total of, you do the math, about 15 minutes, and then another 14 minutes. So this is 14, 15 and 14, 29, and then another, let's say 13. Is that like about 50 minutes or less, 40 minutes? So 50 minutes of video in total, the 3 of them together. I want you to take light notes on the lecture one. Just make sure you have the formulas in there because that helps. But then detailed notes on these 2 videos. Part 1 and part 2. Is that clear? So when you go to, you can click on them. And it should load. Can someone see if they're on their part it loads? Oh, this one loads. This one. Just check and see if on your side it loads.
They all work.
It will. Yeah.
Yeah, they all work.
Most people
Okay.
have no clue that in 2023, the best way to make money on Amazon is not.
Hello, everyone. This video is about work. Okay. So some of the formulas might be repeating of the lecture one, but just remember, if you know all 3 videos, and then take a detailed note of these 2 that are on YouTube, I created all of them. And yep, the level of difficulty of the questions on the exam would be within the examples you see here. Is that clear what you're going to do for your 1 hour and 15 minutes later today? Along with whatever we did together in class. So whatever we did in class, we did it already. So you don't need to do much about that. Just after class, take details note of these 2 videos. Start with watching the lecture maybe first, or yeah, detailed videos of these 2. And then along with whatever we did together, submit it under today's assignment. Yes, Miguel?
So the only thing that's due is those videos.
Along with whatever we did in class together.
Just double checking, sorry.
Yeah, no, that's fine. And today we did a lot of examples, so it should be sufficient. Just, yeah, just the work.
So what we're turning in is all our notes, right?
Yeah, your notes from what we did together, no extra problems there. And then 6-4 videos.
Okay.
But yeah, again, watch 6-4 pretty carefully, take good notes. Again, there would be definitely one question on the test from with the level of difficulty of examples you see on these videos that I created. So if you want to watch the one that I put from YouTube, feel free, but my goal is that you watch these 3 videos that I created myself. 1 lecture and then 2 YouTube videos of myself. Okay. So any question? Thing that I can help you with?